All right, everybody. Josh here with, I think, a pretty exciting product launch. Not a super major one. Not one that's going to, change the world or make you email all your friends in excitement of, can you believe they did that? But one that's super important, and I didn't fully understand how important this was until relatively recently. So bear with me. I'll take you through my journey to this product, and hopefully you end up in the same place that I did. So the product is an anti-seize paste. What is anti-seize? Why do I need it? And why is this little syringe, $20? Well, anti-seize is essentially a high-pressure modified type of a grease that is meant to live in the thread interface of a fastener, like under the head of the bolt, in the threads themselves, or in the interface between like a press fit bearing and the housing that it's in. And it is not grease. It is actually quite different from grease. And that is the journey that I'm going to take you on right now. So let's get started. Okay. My journey here starts with a trip to visit our friends just literally down the street here, Rolls-Royce Jet Engine. And so they are making some unbelievably cool, amazing commercial aviation jet engines, as well as some military stuff. But we have friends there. We've worked with them on our laser welding, some 3D printing things back and forth. And so we've known each other for a long time. And one of the engineers there asked me a question as we were kind of touring the facility. And he said, why does the cycling industry insist on selling people copper anti-seize for their titanium parts? That isn't certified in aerospace. We would never use that stuff. And I didn't know that. I'd never heard. Turns out, if you're in aerospace, nuclear, anything military, submarines, whatever, and you are using multi-material like across the spectrum, and I'll show you the spectrum here in a minute, materials, the anti-seize that you are going to use, because it's the approved one, is nickel. And so I said, I've never even heard of nickel anti-seize. And so we looked it up. We found one of the best aerospace suppliers, actually their supplier. We contacted them, and we got, we made a product out of it. So this is much less expensive than what you would put in an airplane, because it doesn't have the million-mile-long chain of paperwork behind it. So, this little guy, when it's down the street going into a jet engine, is about $250 a syringe. And we're able to sell it for $20 because it doesn't, it didn't have 100 people following it with paperwork for its entire life. But same company, same factory, same stuff. Why nickel? Well, let's think of the problem here. So the base of this problem is that you have some metals, and not all metals, like carbon fibers in there, behave anodically, and some behave cathodically. And for those of you who've remember the physics class or chemistry, remember when you have an anode and a cathode together, especially if you put an electrolyte or put them in an electrolyte together, you have made a battery. And so what ends up happening is you have a material that's way at one end of the spectrum. Like here, we've got carbon, about as far up as you can go. And look at the complete opposite end of the spectrum. We've got aluminum. And for those of you who are around in the late 80s, early 90s to remember the carbon fiber with aluminum lugged frames from Specialized LA was a well-known one, but Vitus and Elan and TVT, they were bonding carbon tubes to aluminum lugs, and within 4, 5, 6 years, pretty much 100% of them fell apart. And they didn't fall apart because they were under-engineered or because they were overstressed. They fell apart because you get a little bit of sweat and a little bit of water in the interface of that bond line, and you start swapping electrons. And what happens is the aluminum basically is giving up its electrons, and you are ending up with this sort of aluminum oxide powder, this white powder that forms at the bond line. And of course, aluminum oxide powder is not structural. And so, your bond line between the carbon and aluminum goes from a bond between two very structural things to a bond between a structural thing and a powder. And that, as you can imagine, doesn't end well. So, in that case, we've solved that in bicycle manufacturing. There's typically a layer of fiberglass wrapped in between them, and a fiberglass is an insulating layer that is very neutral. It's not anodic or cathodic, and so it blocks the swapping of these electrons. The same thing happens in metal, and this is why for years people have gotten aluminum fasteners seized into titanium frames, titanium seat posts frozen into carbon frames, titanium seat posts into aluminum frame, you name it. People have had issues with it. And that is typically, or almost always, this galvanic corrosion problem. Aluminum seat post into carbon frame is a classic one. You sweat on it for long enough, especially like if it's on your trainer and it's seeing continual sweat, it's not coming out. And even worse, what happens in some instances, and you can find amazing pictures of this on the internet, at the aluminum surface where it's turning into this aluminum oxide, it actually takes up more physical volume than it took up when it was just aluminum. And so the seat post is expanding in size and putting outward pressure on the tube, where essentially the seat tube has just sort of exploded in a location from this galvanic corrosion. So one of the things you can do is put a non-electric grease in the interface, and that's a good start. But the problem with grease, particularly in the case of fasteners, is that under the extremely high forces, say, in a screw thread or under the head of a bolt at a moderate torque, those forces drive the grease out. And so, you coat everything up in a grease. You've maybe got, 10 to 100 microns of grease on that interface. You screw it down, it's getting pushed out as the pressures go up, and eventually you are just down to sub-micron thickness of grease in that interface. And so for that to break down, be driven out, or be infiltrated by sweat, it doesn't take a whole lot. And so again, anybody who rides a trainer, all of your handlebar stem, all that, your headset bearing, all of that stuff had grease on it when it was assembled, and if you ride the trainer for 6 months without really cleaning your bike, it's pretty much all seized and ruined. The grease just isn't sufficient. Anti-seize takes a kind of almost our fiberglass insulation direction. It adds a neutral metal to the grease, the very high viscosity grease. And what that allows for is that metal does not get squeezed out of that interface, even at very high pressures. And so, we'll have a little diagram here of kind of a thread. We put our screw, our male into the female. We screw it together. You can see the grease is pretty evenly distributed all over the thread. And then as we tighten, it's getting pushed against the pressure face out into the low pressure opposing face. Same thing at the head, it's getting squeezed out sideways. Now, if we thicken that with a metal, in this case nickel, that nickel under pressure will not move because it's a solid. And so the nickel in the anti-seize can handle these very high pressures without being driven out because it's non-liquid. Does that make sense? Hopefully that makes sense. So why do we choose nickel? Okay, back to our spectrum. So we've got carbon at the top. I've got titanium here at the bottom. Copper's not bad, but look where it is. It's fairly close to tie. It's fairly close to aluminum over here. It's better, but it's not the solution. But let's zoom in. What is right there in the dead center neutral zone? Nickel. Nickel, yeah. And next to it, cobalt, which is like 100 times the price of nickel. So let's stick with nickel. Nickel is perfect for this because it is right in the middle of the spectrum and is super neutral. It's just like our fiberglass interface between the carbon and aluminum lugs that we talked about in our bonding example earlier. So nickel is our optimal choice here when we're threading multiple materials together. So I've got, if I'm titanium into aluminum, right? Nickel it's neutral. If it's carbon aluminum, the nickel is neutral. Really the only time you don't need, or you wouldn't be better off with a nickel anti-seize, is when you are threading like into like. So titanium into titanium, aluminum into aluminum. in those instances, you are just fine to use grease. And so for things like your through axles, right, where you've got aluminum through axle and you're threading it through into an aluminum female thread in the dropout, grease is perfect for that. But when you are, say, threading your steel derailleur hanger screw into your aluminum derailleur hanger, I would use anti-seize, right? All of the threaded hard parts in most every modern frame, every modern carbon stem, all aluminum inserts inside that stem or frame. And so you want to be thinking about that when you're choosing the grease or anti-seize to use. So if your high-end stem comes with titanium hardware, you should really be using an anti-seize on that and not a grease, because it's titanium into aluminum, even though it seems like it's titanium into carbon. The actual contact point, those are all aluminums. Okay, so where do we want to use this stuff? Phil made this killer diagram here. Really anytime you're putting a steel bearing into a carbon surface, anything aluminum press fit into carbon, any aluminum into titanium, really anytime you're crossing the middle of the spectrum, and we have put this chart, this galvanic spectrum, on our website at the anti-seize page, so you can make that decision. Anytime you are crossing the middle of the spectrum here, you really want to be using a neutral anti-seize instead of using a grease. And then anytime you're staying on the same side, or you have two things relatively close to each other, then a grease is going to be just fine for those applications. The one last thing that I want to talk about with anti-seize, and the one place where you might want to use it, even when you're threading like into like, is when you have very torque critical or torque sensitive situations. And the thing about torque, right, is that torque is what we can measure, but it's not really what we're after. Like, we're actually after the tension in the fastener, what you call bolt tension, right? So we're using the amount of torque it takes to tighten the thing to estimate how much tension, how much force is in the fastener, because we can't directly measure force. If you ever worked on like exotic race car engines or motorcycle racing engines, they actually, when you put the heads on, you don't use bolts, you use head studs, and it's kind of like a double threaded stud, and you'll put a dial indicator on the top, and you actually tighten to a stretch, and that stretch is a much more accurate indicator of the amount of tension in the stud than torque is. And why is that? Well, torque, you've got the friction at the threads, and as the torque goes higher, that friction becomes not just higher, but more variable. And then you've got the friction under the head of the bolt, and as the grease or whatever you're using is driven out, that also becomes both higher and more variable. So the other place where an anti-seize can really work in your favor from a torque perspective is in these higher torque, like crank assembly, pedal thread type situations where you really care about having an accurate and repeatable torque value, because the anti-seize is not being driven out of the thread interface or the underhead interface. You're going to get much more repeatable bolt tensions at a given torque level, right? So, there's things you can find out there, PhD papers and things people have written that, for a given torque, you might have a bolt tension variance of 20-25%. Using an anti-seize, you typically drive that down somewhere in the sub 5% variance. So again, very lightweight components, very torque sensitive components. Use anti-seize in that interface. Everything else, aluminum to aluminum, save your money, use a grease that you're comfortable with. Awesome. I think I've covered it all. We just decided to do this video like 15 minutes ago, so it's free form. I don't have a list. I don't even have the actual chart here. Phil's going to put it in. I think at one point I said titanium was down by aluminum. It's actually at the other end. We'll get all that sorted out. But if you have questions, comments, whatever, please drop them down below. If you found any mistakes that I made in this, I'm sure there's some. something somewhere, drop that in below and we will correct it in a future video. Please share this with all the cyclists that you know and all the mechanics that you know. Like I said, I've been doing this a long, long time. I had never taken such a deep dive on anti-seize until the aerospace guys convinced me that it really was the absolute best solution possible for these critical interfaces. And so I want to educate myself, you guys and gals, and your friends. So please tell somebody, send this video to somebody, like and subscribe, ask your questions, and go check out the webpage. You can get the Galvanic chart to begin making decisions on where you might want to use the stuff. And we'll see you next time.